We will continue our study of the convergence of real sequences. The previous thing we have seen was methods like the squeeze theorem, where we had several different sequences and used inequalities between these sequences to find criteria for convergence. So kind of derive convergence for new sequences for convergence from old ones that we already know. In this part of this section, I want to focus on a slightly different thing. Namely, I want to investigate methods for convergence which rely only on this one sequence itself and not comparison to other sequences. So these comparison methods are now, will not be discussed here any further. But we will discuss some other convergence properties. And there is a nice, beautiful convergence theorem for real sequences, which is my next aim, but I will have to introduce some new properties first. So definition 231. A real sequence an, where n and n is bounded from above. So far we've discussed bounded sequences, but this is a slightly more general notion, bounded from above. Because if we have something which is not bounded or something in real numbers, it can either, in the complex plane, of course everything can happen because it's kind of a plane and we have many directions in which something can go unbounded. But if something goes unbounded in R, it either becomes very, very big or very, very small. Or, so to say, so a big negative number of high absolute value. So so it just can go in one direction or the other. And now we want to formalize what happens if it's only kind of escalating in one direction. For this purpose, a sequence is bounded from above if there exists some constant in the real numbers that we call C, such that an is bounded from smaller than or equal to C for all n in n. So we might have negative numbers of very high absolute value, but this doesn't matter. We just have some value from above where it doesn't, which it doesn't exceed. So this holds, and okay, this is bounded from above, and now you can guess what comes next. Bounded from below. It's basically the same as for subsets of R, as we've already seen. Bounded from below, if there exists a number which I call small c in R, such that xn is bigger than or equal to small c for all n in n. Okay, it's basically the same as if we take the set of all elements of a sequence, but seen as a set, as a subset of R. If this set is bounded from below or bounded from above, that would be an equivalent definition, but I just wanted to write this down explicitly. Okay, first of all, an example for bounded from above, bounded from below, and so on. Or a very simple example. First of all, every bounded sequence, bounded real sequence, is both. Because there we know that the absolute value is bounded, and this implies that we have two such bounds. Every bounded real sequence is bounded from above and from below. And another extremely simple example, if we consider the sequence an equal to n, where n in n. We've seen that n is unbounded in the sense that these numbers become very, very big. That was part of chapter 1. But, okay, sorry. Just to check the camera device here because something will look quite fishy. Anyway, an equal to n. So this means this number becomes very, very big, but this sequence is bounded from below because we don't get negative numbers here. So in particular, not negative numbers of very high absolute value. So in this case, this means that this sequence is not bounded from above. So this was the theorem that the natural numbers are unbounded. That was Theorem 152. But it is bounded from below, and as a constant, we can take any small c. So of course this is not unique, so we can take any small c here, which is probably 1 or something smaller. We could also take 0, -1, -1000. It doesn't matter. It's some lower bound. This is then the best lower bound that we can get, so the biggest lower bound. Okay, very simple example, and if we just would take in the same way, if we take -n, over n and n, we will get that it's just the other way around. It would be not bounded from below, but bounded from above. This is, I hope that's quite obvious. Okay, this is one property that we need for the next theorem. And there's one additional property. Okay, again, that n in n be a real sequence. Okay, part 1, I call it A. The sequence an is called monotonically increasing. That's probably some term that many of you have already heard somewhere in high school or wherever. Monotonically increasing if the different elements of the sequence are just becoming bigger when we follow n, or stay the same but never become smaller. And this formally means it's monotonically increasing if an is smaller than or equal to an plus 1, and if this holds for all n in n. Okay, now it's everyone's guess what comes next. We have the similar notion, of course, the sequence is just going down or staying the same, but not going up. And this is the notion of monotonically decreasing sequences. So n in n is monotonically decreasing if an is bigger than or equal to an plus 1 for all n in n. And just to summarize these things, we call the sequence an monotonic if it's either one or the other. So just to summarize these two cases, it's monotonic if it is monotonically increasing or monotonically decreasing. Okay, monotonic. This is an important property, and there are many sequences that we've already seen that are monotonic in some sense. So let's give me some examples of monotonic or non-monotonic sequences. Example 234. First of all, the trivial example. Of course, we always start with the boring one, namely any constant sequence is monotonic. This is trivial. Any constant real sequence this is, of course, monotonically increasing and monotonically decreasing. And it's kind of trivial to see that these are the only sequences which are indeed both. So if we have a constant sequence, we always have equality between all elements of the sequence, and so especially we have the inequalities. Secondly, another very simple example. We just take again the sequence n over all n in n. Of course, if n is getting bigger here, this is getting bigger as an element of R. So this is, of course, monotonically increasing. And minus n, just the same way. If the numbers become bigger and we put a minus in front of it, it reverses all inequalities. So this is monotonically decreasing. Okay, now we another example of a sequence which is not monotonic at all, namely the sequence an equal to minus 1 to the power of n that we've already seen. This is kind of the sequence which is jumping between minus 1 and 1, doing nothing else. So n in n, and this is not monotonic. It is neither monotonically increasing nor monotonically, no comma between here, I'm trying to be precise, monotonically decreasing. And just for the formal argument, okay, this is jumping between 1, minus 1, 1, minus 1, 1, minus 1. Whenever we jump from minus 1 to 1, we are of course increasing. And from minus 1 to 1 is always, we know that if n is an odd number, this is minus 1. If n is an even number, it's plus 1. So this is the case when we're jumping up. So a 2n minus 1. It's not just some standard way of writing odd numbers. This is always smaller than or equal to a to n. for all n. But if we now go one step further, if we start at a2n, this is the case where we have +1, then the next term of the sequence is again -1, so we are dropping, we're decreasing again. So a2n is bigger than or equal to a2n plus 1, so it's going up and down and up and down and up and down, which is kind of the opposite of monotonic almost. So, but this holds for all n in n. So this is not monotonic at all. Okay, these monotonic sequences have a special property, or not special property, but if we take a look at these are unbounded. They are kind of, this is growing into oblivion. So this is growing and growing and growing. They are really becoming bigger and bigger and bigger, and this is becoming smaller, 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 but they are unbounded. They are just bounded in one direction. And we will see that the monotonicity plus a boundedness condition already implies convergence, which is an extremely useful theorem that we shall see next after I've erased the blackboards. Before we come to the theorem, I want to give you some intuition and some visual illustration of this property that I want to discuss next. Namely, I want to kind of draw the graph of a sequence. Real sequence means with each point in n, we associate a value in R. And you can just draw them here as points in R2, or this is just some coordinate quadrant. And the idea is now, if we have a monotonic sequence, this means we start monotonically increasing, for example. We start with some value here, which would be A1, this would be the first part, and now we know that it's just somehow increasing. We don't know how much, but it's increasing. Now, let us put another condition on it. Namely, we want to assume that this is bounded from above. This would mean that we would have here some y value, that's called a c, and assume this is the upper bound, so that if we would draw the horizontal line here, we increase, but we never exceed this line. Okay, if we now take a look at this, so we know that these points either stay constant at some point or they grow and grow and grow and grow. But we know if it stays constant, it kind of course, it converges to some case. But if it goes up and up and up, there's some point where it can't go up any further. So it can't go up too much. This means kind of, it has to kind of, the speed here is to slow down, so it has to become flatter and flatter. And this, like if it would go on like this and like this, you might know, okay, they have to now, there's just no space. It can't just go beyond anything else, and this has to grow towards some value, and this means it should converge. So this would be an example of something converging against this upper bound C that I've drawn here, where the points would like go on like this and this and this and so on. And of course, the only way we could kind of escape from this convergence would be if something would then again jump out or jump away from this value, but this can't happen because it's monotonic, so we cannot have any setbacks. So it's this cannot happen. And this is the idea, that if we have something which is monotonically increasing and has an upper bound, it must already converge. And the same thing dually, if we kind of would turn this picture upside down, if we would have something which is monotonically decreasing and bounded from below, we were in the same situation. So this is exactly what's the content of the next theorem. Theorem 235. So let an be a real sequence. N and n be a real sequence. Part A, if the sequence an is monotonically increasing, increasing and bounded from above, then an is convergent and not only that, we can kind of write it down, sorry, I shouldn't speak and write at the same time, with the limit can be formulated in a different way without using the word limit, namely the limit of the sequence. We know that it's getting bigger, 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 and then coming to a halt sometimes, or somehow. And this means if we look at the sequence of, the set of all elements of the sequence, so the set of all an where n and n, we know that this is kind of coming to a standstill at some point, and so the point to which it converges to, this can be then simply described as the supremum of this set. So we really can determine the limit here. And the same way, as I said before, the same holds for the other direction. B, if n in n is monotonically decreasing, decreasing and bounded from below, then it also converges. So then n in n is convergent, and the limit is also expressible in a different way. Namely, if we know that now if you understand this, you will probably can already tell what's coming here. So if it's going down, 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 and then approaching some value, this can also be described in terms of this set. This is simply the infimum of the set an, where n in n. Okay. This is, in my opinion, one of the most beautiful theorems here about sequences, because this kind of makes proofs of convergence sometimes much easier. Because you know, when you want to show convergence, as we've seen before, we need for each epsilon, we need to find some n0, which mysteriously works out so that we can get everything inside a zero bound around the limit. This is, of course, not that easy. And in general, it's kind of, there's no general method, and you have to try and do with each sequence individually. But here we've got some other conditions. So here we need to check that something is bounded from above. Well, that's not too hard usually, and that's monotonically increasing. So we need to prove some inequality. And this is something you can really check. You can really write down and prove these things. So there are many examples where these two conditions are checked much easier to check than the convergence itself, with really by definition with this epsilon neighborhoods and so on. Okay, let's prove this. And I will only prove part A, since part B is basically proven in the same way, just by reversing all the inequalities and replacing supremum by infimum. I will include a proof in the lecture notes. But if you really want to try it, so take a look at this proof of part A and then pause the video and try to work out your proof of part B by yourself, since this is then kind of following the same lines, so you can see if you understood things. Okay, so first of all, we know by assumption the sequence is bounded from above, which means that the set of all an, where n in n, is bounded from above. This follows just from the definition. And we know that we've seen kind of that's the way we defined the real numbers, that every subset bounded from above possesses a supremum in the real numbers. So since this is a bounded set, we know that the supremum really exists as a real number. So S, which we just shorthand notation for the supremum of this set, and this really exists in R. Okay, and we want to show that this is indeed the limit of the sequence. Okay, and this is really now a beautiful proof in my opinion, because we really just need elementary stuff from what we did before, and this is kind of quite instructive to understand what's going on. So again, we start with taking some epsilon bigger than 0, and so we need to show that we come epsilon close to S with the sequence from a certain value on. First of all, if we have any epsilon bigger than 0, we know that the supremum is by definition the smallest upper bound. So S is the smallest upper bound. We know that if we subtract epsilon, so if we take S minus epsilon, this cannot be an upper bound. So since this is the smallest upper bound, there exists some element of the sequence, so there exists an n0 in n, such that this element a n0 is bigger than S minus epsilon. So there exists an n0 in n with S minus epsilon is smaller than a n0, which is of course bounded from above by S, since S is an upper bound. So this we can always find, but this was here we needed the boundedness of the sequence, and now the monotonicity is now the key argument here. Since S is an upper bound, and an is monotonically increasing, this shows, so this yields that if we have S minus epsilon, and now we have seen that a n0 is bigger, but if n is now bigger than n0, we cannot go back beyond a n0. So this means we always have an inequality like this as soon as n exceeds n0. And we know, since S is an upper bound, that this still holds for all n bigger than n0. And this now shows that really this an is caught in between S and S minus epsilon, so in a very small neighborhood of S. And this already shows the convergence. Intuitively, I think this is clear now. So in the picture, whoops, Jesus, sorry. obstacles in this room. Okay, we would be this would be, instead of C, this would be S, the supremum of the sequence. And now if we would take S minus epsilon, so say we have some epsilon, draw it a bit big so we can see, this would be S minus epsilon, here we would have F plus epsilon. And by our definition of convergence, we know that, let me take a different color. If we draw some strip around this limit here, so something like this. So the convergence definition says that our sequence has to be within this blue strip from a certain point on. And this is precisely what we've shown. We've seen there is, because this cannot be an upper bound, there is some element which is kind of inside the strip. But once we're inside the strip, we are kind of caught between this limit here and the lower bound here, so the lower edge of the strip. So this means everything has to take place here in between. And this shows that we are inside this epsilon neighborhood. And since epsilon is chosen arbitrarily, this shows convergence. And this we need to just write down formally. So we've seen this. And this now implies what we need to show is we need to estimate this absolute value, the difference of an minus s. But we've seen here that s is always bigger than or equal to an. So the absolute value of this is always given by s minus an. Okay, but if we now use this inequality, so we have an bigger than s minus epsilon, and if we now have a minus in front of it, this changes the inequality. So this means this is smaller than s minus epsilon, which is of course epsilon for all n, at least n0. And this shows convergence. So since epsilon was chosen arbitrarily, this shows the convergence. So this shows that the limit of an is s. And this is what we wanted to show. And part B, with the infimum, as I said, you might now pause the video and kind of try to work it out on your own. Otherwise, you'll find a proof in the lecture notes. But I kind of recommend to try to solve this your own, because it's kind of quite instructive and you can really see if you understood the method here. Okay, yes, this is now a nice convergence criterion. And as the next thing, I want to introduce a class of sequences, or kind of a way to describe sequences, where this theorem really has some nice applications, where it's really typically used, and this is what I want to discuss in the rest of this video, namely so-called recursive sequences. And yes, let me give you, again, a hybrid of theorem and definition. 236. So again, very general. We again study a set. So this time we kind of do this general thing with sequences and sets, and we take any map which goes from X to itself. So this is just some map, and we take one fixed element A of X. Then there exists a unique sequence in X. Unique sequence an nx with the following condition: A should be our starting point. So A1 is equal to A. And to go from there to the next value, we shall use f. Namely, we just want to say if we want, if we have A1, we want to get A2 by applying f to this A. Then we want to get the next element by applying f to this element A2, and so on and so on. And this is simply described by saying the n plus first element should be just f applied to the nth element. And this for all n in n. So this is where I describe the sequence. So instead of just really writing down some explicit equation or something for the sequence, we just say, okay, if we have one element, we work our way to the next element, then we'll work our way to the next element, and so on. This is, of course, much more indirectly given as in the previous case, but this is sometimes really kind of a natural way of how to describe things. And we will see some examples for this later on. So a sequence, and this was the theorem part, now for the definition part. A sequence defined by this property, so by having this property here, is called a recursive sequence, or recursively defined sequence. So instead of writing down in the sequence in explicit detail, we can just write down some recursion formula like this. And so we get a sequence. Okay, the proof is extremely simple, so let me just squeeze it in here. First of all, you might ask what's there to prove, and this is kind of, the answer is not much. First of all, the uniqueness is clear, because if we kind of can work our way through the sequence and have this equation written down, this has to be unique. This already determines everything. So uniqueness is obvious. Okay, and to show that this really defines a sequence, this is very simple. Existence by applying the induction principle from the first chapter. To the very simple set n in n, for which an is well defined. And this recursion formula simply says that this kind of inductive set. And yes, if we apply this induction principle to this particular set, this really shows us that this set has to consist of all of n, and then we're done. So this really, just to be really precise, this shows that this really defines a sequence. Okay, after erasing the backboard, I will first give you some example and then some very nice applications, which takes a little more effort to prove, but which has some really interesting results. We consider a very simple example of a recursively defined sequence where you can see kind of how recursion appears naturally in some situation. And of course, there are much more complicated situations in which this also happens, but this is now the kind of simplest, non-trivial example I think I can get. Okay, first of all, we think about money. We assume we have some fixed amount of money, so let's say A euros. So A is just this value here. And assume we have this on a bank account with a fixed interest rate. So in a bank account, which has a fixed annual interest rate. So if I leave it on this account for 1 year, I will get a fixed rate P% interest on this money. Of course, nowadays P is very close to 0, but anyway, put A in the bank account at fixed annual interest rate. Oh, sorry, annual interest rate of P%. Okay, if we now define a sequence by letting just A be the amount of money in the account, in year n. Okay, so n could be very big, so of course having a big amount of money lying in an account for n years or something, this is not something which is natural for students, but just imagine the situation. So we have some money and we have it as a fixed interest rate. So in the first year we will just have the starting money because there's no interest yet. So A1 is the same as capital A. Then, to go to the next year, we can just describe this recursively. Namely, if we have something in year n and leave it there for another year, then we would get the interests again. And to get this interest, this means, so in the n plus first year, this will be an multiplied by some number, namely we take first 1, so the capital of course stays the same, and we get some additional interests. And the interests, if p is the percentage rate here, we would get plus p over 100 times an, and this for any n in n. So this really is something recursive because this interest rate precisely describes what happens from 1 year to the next. So this is the procedure here. And of course, for everything, also I could have chosen like viruses or something, for example, so if you have some growth rate. So if you have something growing, you can also describe this by this recursional way because these growth rates show kind of how something grows within a fixed amount of time. And so kind of this is how you can, really have these procedures, and this is kind of, so the recursive sequences really appear naturally in these situations. Also, maybe if you have some, I don't know, some gas kind of growing in some fixed containers, you can kind of, if there's a fixed amount of gas coming in there every minute, you can also describe this growth of the gas, of the amount of gas in some container by such an equation anyway. So this is an example of a recursion. And here we can see that it's also, I mean, this is really simple. You can really find an explicit formula for this. And usually if you want to prove really a formula for such a recursive thing, you usually have to prove this by induction. In this case, this would be really easy, and I will not carry out the details. Proof by induction that the money in year n, so if we just, every time we multiply with this, we just have to multiply often enough, and this means that an is 1 plus p over 100 to the power of n minus 1 times a, times the starting value. So to get the money after n years, we have n minus y times multiplier, multiplier, multiplier. So that this really holds for all n and n. Okay, there's also a name for this. If we have a recursive sequence, and we can find a sequence like this where there's no recursion anymore, but we can really describe an in terms of n with an explicit equation, this is called explicit form, the explicit form of the recursive sequence. So this means, i.e., an described just in terms of n and not with respect to some previous values. Of course, such an explicit form is preferable, namely, if we only have a recursion formula and want to kind of compute the 100th term of the sequence, we have to compute the first 99, because we just have to get to number 99 to get to 100. But to get the 99th, we need the 98th, and so on. So there's a lot of computations involved. And of course, like if we want to put this in the computer, there would be a lot of some loop which kind of computes with a lot of iterations. But this would then really be some formula where we can just put in a number and bam, we have it. So this explicit form, these things are sometimes really, much better, but they are sometimes also very hard to find. And the good thing is, if you just have this recursive sequence, which is defined in some way, and have no clue what the explicit sequence looks like, the previous theorem that I had of monotonicity and boundedness, this really often helps you to show that some sequence converges, although you cannot write down the sequence explicitly, which is something which is very useful, and you will see examples of this in the exercises. Okay, second example, just I want to spice things up here by a little bit. Assume we have a very generous bank, and assume that additionally the bank puts €1 into the account per year as kind of a loyalty bonus or something. The bank adds €1 per year into the account. Okay, what's the difference then? Also very simple. A1 is of course again A, since we just start with the basic the money we put in. And in the n plus first year, we have again the same interest and so on. 1 plus p over 100 times the money that was in there in year n, plus €1 on top. So just adding 1 here at the end. But here it turns out that the recursive sequence, the recursive form, which is just this neat formula, this is often also much simpler than the explicit form, because writing this down explicitly is a bit of more work, which could then be simplified, but I just want to give you the example here. So in this case, if we just would compute the terms explicitly, so explicit form. So let us first compute maybe here on the slide, the first ones to see what happens. So A2 would just be 1 plus p over 100 times a plus 1. But if we then would put here A3, this would already be, so multiplying this with 1 plus p over 100. So we get 1 plus p times over 100 squared times a, plus 1 plus p over 100. That's for multiplying this with 1. And again, you get the additional euro that the bank puts on top. Okay, if we do this one more step, we have to multiply all of this with 1 plus p over 100. So 1 plus p over 100 to the power of 3 times a, plus 1 plus p over 100 squared,
plus 1 plus p over 100. This is multiplying with 1, plus the bonus by the back. So, and so on and so on and so on. And if we want to have an explicit form for this, you can again show this by induction, which is also not that easy, not that hard in this case, that an is 1 plus p over 100 to the power of n minus 1 times a plus the sum from k equal to 0 to n minus 2, 1 plus p over 100 to the power of k, but this time we have to start, at n from n bigger than or equal to 2. So A2 can then compute it by hand. It can be computed by hand, which we have done on that side. So this is then the explicit form of the sequence here. This here could be simplified. This is kind of a geometric sum, as we shall see later. But just to motivate here now, this explicit form can become quite messy in some sense. So sometimes recursion has its advantages. Okay, this was an explicit example, and now I will present you another beautiful application of these things and to see what recursive sequences can do. Namely, I present you a theorem which is actually about almost 2,000 years old. I think it's from the, I've looked it up, it's from the 1st century AD, so yeah, very old, from old Babylon. It's called Heron's method, or sometimes Babylonian method, but I will use Heron's method as the name. Namely, of course, the Babylonians didn't do this with this formalism of theorem and proof and so on, but the main idea, so this approach works. Namely, we get an interesting recursive sequence. We take a positive number a, and we consider the following sequence given by a recursion. We start with 1. In fact, I've simplified things a bit. Here could be any positive value, I think. But I'll just start with the value 1. And we just say that xn plus 1 is supposed to be 1/2. And now something in terms of xn. This is 1/2 xn plus a over xn for all n in n. Since we start with something positive, and here everything is positive, so xn does never get 0. So then, of course, this would be well defined, but this doesn't happen here. Okay, this is an interesting looking sequence, and this kind of, you might wonder what happens. And then, as we shall prove now, xn converges and has a very interesting limit, namely the limit of n to infinity of xn is the square root of a. That was unexpected. So this is an amazingly beautiful theorem, because if you think about this, when you want to do computations with a computer or some computing machine or whatever, what computers can do good is the elementary applications that elementary operations that we have in the field, like addition, multiplication, and these elementary computation methods. What computers can't do that good is kind of putting square roots or something. This is some advanced thing, because also roots are defined indirectly. They're kind of the unique solution of some equation and so on. And this is very hard, and you need a lot of computations. And this is kind of an approach how you can really approach these square roots by simply defining such a sequence. And you can see this is kind of nicely for a computer, because this really just involves addition, multiplication, and division, which is the same as multiplication with inverses. But this is something that's really elementary operations here. There's no roots involved. We just take the field operations that we have, and we're good. So this is kind of a sequence which you can really compute. And afterwards, we shall now prove this theorem, and then afterwards I will give you an example, and we will check kind of how good this convergence is. And we will see that it's surprisingly, this converges surprisingly fast. So already, after a few terms, we get some very good approach of some square root, as we will see. Okay, let me quickly erase, and then we'll do the proof. The strategy of proof for Heron's method is that we want to apply the theorem I had on the board earlier, and to show that this sequence is indeed bounded from below and monotonically decreasing, which then implies convergence by the previous theorem. So we want to apply several steps. So the first step is just some intermediate step, which we just need in what follows. So I will first prove 3 different steps on their own, and then do the general argument. First of all, as the first claim I want to prove, is that xn is positive for all n in n. This is something I mentioned already, and this is almost obvious, but technically we really have to be precise about this. So proof of this small claim. And as everything involved with recursive sequences and all the properties, or not everything but most of it, we do this by induction, because induction and recursion really go hand in hand. So by induction over n. So the base case is clear. So to remember, this was n equal to 1. Yeah, so we need to show that x1 is positive, but by definition x1 is 1, which is certainly bigger than 0. Okay, done. Induction step. So we assume that xn is positive for some n in n that we have given. Then, okay, let's take a look at xn plus 1, and we just have to take a look at how it's defined. This is 1/2 times xn plus a over xn. Okay, what's happening here? xn, this is bigger than 0 by induction hypothesis. Okay, now I've got, don't have space here. Okay, this as well. So here, same argument, xn is positive and a is positive by definition. So this is positive, this is positive. So we have only positive numbers involved, which implies that this is positive, which then proves the claim. Let me just mark the end of this sub-proof here with this symbol here, with these two lines. Okay, first of all, so these are positive. Secondly, I want to show that xn plus 1 is bigger than or equal to the square root of a for all n and n. So this means from the second term on, the first one is of course 1, but from the second one on, we are always bigger than this a. Okay. Yeah, now you might ask, okay, why did you then prove this when you want to prove something stronger here? Because we will need this in the proof of this. So this was just some subset. Okay, here we don't need induction because here we can now use part 1. Namely, by 1, since we know it's already positive, it suffices to show that the square of xn plus 1 is bigger than or equal to a. So this is what we need to show. And yeah, of course, because it's a positive solution, so this yeah, we cannot have the difficulties that we would have something negative here, which would kind of revert the inequality. But if this is true and this below is positive, we would then get the same inequality for the square roots as we've seen, and the square root of this here would then be xn plus 1. So there's no sign issues at all. So that this holds for all n and n. Okay, and this we can easily compute. Not easily, but we can compute this. Okay, we take xn plus 1 squared. By definition, or by the recursion that we have here, this recursion step, this is the same as this 1/2 xn plus a over xn squared, which is of course the same as 1/4 of this term in parentheses squared. Okay, and if we compute this, simply by using the standard formula for these quadratic powers of some sums, this is 1/4 xn squared plus twice this times this, and of course these two xn cancel each other out, so the middle term is just 2a plus a squared over xn squared. Okay, now we do a trick. Namely here, we see that if you have 1/4 in here, we have, this is, if we would multiply this, we would get a over 2. Now we do a trick, namely we draw some fixed term a out of this parenthesis. So here we've got now, this was a over 2, so we've got here a over 2 too much, and we need to put this back in the equation, and this then into the parenthesis, and this looks then nice in this following way. This is the same as this xn squared, okay? Right? This is just here a minus 1/2 a, which is plus 1/2 a, which is the same as there. So this works. So we want to show that this term here is bigger than this one, so all we need to show is that this here is non-negative. But if we take a close look at this and compare it with this, what we computed, this is again also the product, some quadratic power here. This is the same as a plus 1/4 of xn minus a over xn squared. But this is a square. We have seen that squares are always non-negative. 1/4 is also non-negative. So, of course, this is non-negative, which means that everything here is bigger than or equal to a. And this is what we wanted to show. Okay, so much for that. So we now know that we have this boundedness from below. So this shows it's bounded from below by this number square root of a. Sorry, apart from the first term. The first term is 1, but since we're talking about convergence, when the first term does something that we don't want, we don't care, because we can basically just start considering the sequence from term 2. Now this gives us boundedness, as we shall see, and now for the third thing, the third sub-proof or sub-conjecture that we want to put in here, namely we need the monotonicity property. So we need to show the following: xn is bigger than or equal to xn plus 1 for all n bigger than or equal to 2. Okay, and this can also be computed. Namely, this is actually surprisingly simple. So proof of this. Oh, sorry, should write it a little bigger. Compute for each n at least 2. Okay, compute the difference between xn and xn plus 1. So we need to show that this is bigger than or equal to 0. Let us write this down. This is xn minus, by the recursion, 1/2 of xn plus a over xn. Okay, and if we multiply this and subtract from there, we get that this is the same as 1/2 xn minus a over 2xn. And if we now put this onto a fraction and expand this to a fraction, this then gives that this is xn squared minus a over 2xn. Okay, and now we're done, because this here, this is bigger than 0 by 2. This is what we have just, bigger than or equal to 0 by 2, which we have just shown. This is positive, so this is bigger than 0, and this shows the monotonicity property. So we've got this. So we know that from the second term on we are bounded and monotone. So we've seen it follows that if we take the sequence xn plus 1, n and n, this is monotonically decreasing, monotonically decreasing, bounded from below. So this immediately gives us by the theorem from before. This was Theorem 235 part B, that xn plus 1 is convergent. And of course, there's just one term missing. So this would technically be a subsequence of xn, but if there's just one term missing, of course, the whole sequence would converge against the same value. So this shows that xn is convergent. And so we now know already the sequence converges, but we still haven't shown that this really converges against the square root. So how do we see this? There's also a nice explicit method. Namely, first of all, we define this limit as, I just name it capital L. L for limit. Okay, this should be the limit of xn. And of course, since this was only one part missing, this is the same as the limit of xn plus 1. Okay, and the only thing we know so far is that this is bigger than or equal to the square root of a, because we've seen in part 2 that all terms of the sequence, so all of the xn plus 1, they are bigger than or equal to the square root. And we've seen in the corollary, I haven't, what was the number? I don't remember. If a sequence converges and all of the terms of the sequence are bounded from below by something, then the limit can also not exceed this as well. This was a consequence of the squeeze theorem. Let me quickly corollary 227. I already need to erase, and then then we'll see. Okay, we have the limit, which is bounded from below by the square root of a. And now we can then use the recursion formula of the sequence to really compute the limit, which we shall see now. So then it holds that L is the limit of n to infinity of xn plus 1, which is then the same by just inserting here the recursion formula as limit 1 to n to infinity of 1/2 xn plus a over xn. And since we now know that the xn are already converging, we can use the computational rules for limits that we have seen. Namely, this is by our laws from the previous section the same as, by the rules for limits from the previous section, this is the same, so the 1/2 can be put outside, and then we can take the limits of the two sums. The first one is then just limit of xn n to infinity, and here we have the limit of the quotient, which is then in this case also this converges, this is constant, so we just get that this is plus a over the limit of xn. But now this limit of xn, this is of course again L. This was how L was defined. So this is 1/2 of L plus a over L. Okay, now we get a rule of how to compute L. Namely, we have shown that L is 1/2 L plus a over L. We know that L is positive, so this is all here fine with the quotient. And so if we now multiply both sides by L, we get that this is equivalent to L squared is equal to 1/2 L squared plus a. So if we multiply by 2, we get 2L squared is L squared plus a, and this is of course the same as L squared is equal to a. And this means, by just solving the standard way of quadratic equations, this has two solutions in R. Technically, I haven't proven this, that we have two solutions of these quadratic equations here, or at most two solutions. I might do a little later, but the solving of quadratic equations, we get two solutions. We get either L is equal to the square root of a, this is basically some high school math here, or L is minus the square root of a. But we've already seen that L is bigger than the square root of a. So this bigger than or equal to the square root of a, so we know what it is. Namely, this shows that L is equal to the square root of a since L is bigger than or equal to this one as shown before. And this is what we wanted to show. So we've shown that this sequence really converges against the square root of a. So we have now this method, we have really a nice sequence, a recursive sequence which computes the roots. And the question is of course now, okay, I can write down something that converges against the roots, but what if I have to compute 1,000 terms of the sequence before I get my roots? Well, this wouldn't make it more efficient. So let's take a look at an example. And we will just take a look at one value, but let me say in general, I mean, you could study this in detail, but you can show that this, this really converges remarkably fast, which is why I call this a remark. So this is a remarkably well converging sequence, namely, so Heron's method really gives a good approximation. Good approximations of square roots. So again, this would be kind of a form of how to approximate square roots by elementary computing operations, and so would be helpful in using computers and so on. Okay, let me consider a fixed example, namely a equal to 2. So the square root of 2. You might remember, I haven't discussed this here in the lecture, but that this is really an irrational number. So we know that the square root of 2, so let me put no in quotation marks. So we know from high school maybe that this is really an irrational number. So it's actually not that easy. So let me just write down the first digits of the number. So now I'm doing something that I usually will not do in this lecture or try to avoid, and computing things directly by decimals or something. This is something, I mean, as soon as you write down decimals, you have to kind of round up things and down, so it's not really exact mathematics what we want to do in this course. But this is then given by 1.41, oh, let me just I hope in case you don't know, in America it's usual, or in most countries it's usual to use a point here. The German style is to use a comma. So 1 comma is the same as 1 point in the US. So I think that the meaning of comma and dot in the numbers are just the other way around as in America or as in many English-speaking countries, I think. Okay, the square root is given by 1.4142, and so on. So we are mathematicians, numbers don't matter that much to us. Okay, I'm just writing this down to check how good the convergence is. So let us write down the first terms of the sequence. So the first term is 1, which is obviously not a good approximation, but let us check what happens next. So x2, this is by definition then 1/2 times, and then x1 plus a over x1. So a is 2, so this means we get 2 over 1. This is then 3 over 2, which is 1.5. Okay, already better than 1, but still not what we would like to have. Let's take a look at number 3. This is 1/2 of, and now we have to insert this new one, 3 over 2, plus 2 divided by 3 over 2. And yeah, this is of course 4 over 3, and if you compute this, you will get that this is 17 over 12. And this is already surprisingly well. This is 1.416666, and so on. So this is already not bad. 1.144, 416, and of course, in practical applications, we always need to kind of find out if we want to really do some computations, how many digits we need. So how far after the comma should we need to consider, and what approximation is good enough for our purposes. So this might also be for very rough things where we only need the first 2 digits here. This is already a very good approximation here. The good thing is also we get rational numbers here. And rational numbers are also something that are easier to handle than some strange irrational numbers, of course. Okay, let's take a look at the fourth term. And this is the last I want to compute. This would be 1/2 of 17 over 12. And then we would get 2 divided by 17 over 12, which is 24 over 17. And this is something which takes a while to compute, as I found out. This is 577 divided by 408. And if we put this in a computer, this is 1.41421568, and so on. This is really good. Here we can see 41421, these are already correct. So the error is very small, even after basically the third iteration step that we did. So this shows that the difference of x4 and the square root of 2, this is then, so these are almost approximately 2.10 to the minus 6, which is really not bad. I mean, this is something, which is very good. Of course, how in general this works, if we can approximate square roots in general and how much these iterations deviate from the square roots that we want to consider, this is something that you can also investigate. We won't do in this course, but there is some theory about this, and you can kind of decide how bad it can get, or kind of how many iterations of the sequence we need to compute to approximate a square root or up to a fixed number of digits that we want to have in our computation. Okay, this was a bit more, at least something with numbers involved. So, this was everything for convergence of real numbers. And in the next section we will, real sequences, sorry. In the next section we will still study real sequences, but we will then study other properties that are not directly related to convergence, but also we will study divergent sequences of real numbers and see what happens with these numbers, what we can do with them. See you in the next section.